So you want to store the data. So actually, as much thin is there, as that much would be fine to you. So these are the primary purpose of thin films. Now, what are the advantage actually? Advantage is that first they need less materials, so you can cut down your cost. Flexible because they are thin, so they are means malleable. You can bend it as many times as you want. They won't break it also, so non-breakable. These have a lot of these applications these days actually. In case of your PVC banners, your flexible, and these days people also make your vehicle number plates also. Those are also those thin films only. Then, because as your barrier in case of the electrical vehicles or batteries and all this, so as you will make your barrier thinner and thinner, you can apply very high voltage. So it can sustain high voltage from there in that case. Now, fabrication point, simple actually, it looks simple, but it needs the very high end, means the equipment just to make the thin films. The infrastructure wise, actually, to cell support, so you don't need much at that particular end. So, and moreover, actually, the temperature part. So, temperature is generally the room temperature something, so you don't need excessive energy at that particular end, actually, as far as formulation part is concerned. Now, these are some applications of the thin film where you have lithium batteries here. So, the first lecture was there on fuel cells, hydrogen energy, electrical vehicles, and all this. So you have in that these days you are putting, because this thin film, once your batteries are damaged, you can easily replace the cell actually in that way. Solar panels, because earlier time all solar panels were of glass actually, and those were very fragile. So these days you have a solar panels with of actually your this polymer films, and those can sustain any sort of wear and tear. Even if you will bend or they fall down, they don't break. I mean anything, nothing happens in that case. Now, transparent film, these are being used to make your ID cards, your panels, also digital panel, display panels, means also you can use that. And blood samples these days are also being used in terms of tubes. These are also thin films. All glass tubes has been the replaced these days because due to fragile characteristics of glass. Then optical coating, just to have that your optical properties, just like optical fibers and all this. So optical fibers, these days your intensity of the signals will not deteriorate. You will get 100% total reflectance of the material if you have coated it properly. Then you have household applications. Wherever you have very cold climate, actually you want to store some energy. So you want a coating which can absorb the light. And second thing, in case of very hot climate, where you don't want that outside heat to come in, so you want a reflective coating so that 100% light should be the reflected back actually. So you can design the coating as per need. Now, what are the objectives of the drying? First part is drying just to dry the wet product and just to get the final products. And then how do we need the drying? Practically in household, daily use applications or all domestic paints, we apply the paint and leave the over the period of time. That is one. And in case of industrial part, we cannot leave it just like open, because you have their dust particles, so many other particles. And if they stuck to your wet materials, so actually your product quality would also deteriorate. So in that case, what you will do, you will have industrial ovens or dryers for that particular purpose. Now, then you have in those dryers, you have to flow the hot airs, and you have to control the temperature, your blowing velocity. By chance you have a wet film, wet materials, if you are blowing the air at a very faster rate, So in that case, you will have some bubbly type of characteristic on the film. You don't want, that is also the defect. Then moisture, just like in case of daily house, means painted, if you are painting your house in case of the rainy season, you will find the quality of film once it is formed is very bad. It's only because of that it's not dried properly. It has rather it can absorb the moisture from atmosphere and your coating may fall down actually. That can also happen in the industrial dryer also if your dry air is not dry or if you have some humidity problem in there. So that is one part. Second part is modeling, just to model them, find the optimum because what we have talked about air flow rate, velocity, moistures, and drying time also. How much time should I give in a particular temperature or air flow rate? So I have to optimize all of them so that my final product should be a good quality one. So it's the last and most critical means the step that need to be taken care and with some examples of audio tape, video tape, adhesive, photographic films. Then what are the important features of the drying? Drying, you actually what you need here, the particle size or film size may vary from microns to 10 centimeter thick. And you have also your wood logs and also those are much more thicker. They are in fit your wood materials, your wood actually, your dry wood, means that also need a controlled drying. Because in case of wood log, if your drying is not proper, it will crack actually. So that's only because of that. By chance, you have very high temperature on the outside. Inside, you have very large amount of the moisture. So if you will not match the rate of the evaporation of the solvent from the surface and the diffusion of solvent within the material itself, be it food material, be it your wood materials, you will find a cracks there. And then porosity. So porosity also need to be controlled. Some materials are zero porosity, just like solid materials, your glass, your metals. Some are 100% porous, just like your tissue papers and all this. So, the paper materials. Then drying time. So sometimes you need a very fast drying, just like let's say 0.25 seconds in case of the tissue paper. Sometimes you need months, just like your wood logs. Actually, wood logs take over a period of months actually to get a perfect quality of log. Then capacity, at what rate they can be produced actually. So you will have 0.1 kg per hour to 200 tons per hour actually. So that's in case of the paper rolls and wherever the films are blowing in the paper industry. Then the speed also, how much speed the things will move actually in the case of dryers. So all of us did some practical in case of sand drying in our mass transfer lab. So we just put a tray there, we blow the air, that is one way. Next way that we are maintaining some condition in a particular chamber. Now we are passing on our materials in that particular section actually, so that the speed also need to be controlled. Then again temperature, so we cannot have a temperature which may boil the materials or the solvent, because once boiling is being done, then your product quality will again deteriorates. Then heat transfer, how do you want a continuous the heating of the materials, or you want the heat for some time then just blow the air, so you have to control that part also. Now, the method of the drying means how can we dry it? So the most commonly people use this, the natural, the drying. This we use for daily use per household product. All food materials, once we do the harvesting of the crops, so we do the natural drying actually. So primary drying for all food materials, the natural drying actually. There we do two type of control. Either we do the sun drying, we just leave the things in the open, or we do the shade drying, because shade drying will help you just to retain the texture or color of the materials. Because if you will just directly give to sun heating, due to the UV rays or the high intensity of the light, that can actually fade your color on the top surface actually. Sometimes the cross-linking can also happen. So open sun drying for some of the materials are not allowed. So you go for say drying just if you want to retain your color. Same thing happen for your very good quality fabric cloths also. People put a tag on that. Use the shade drying. Don't do directly in sunlight because there you have a coating on that particular fiber and that will actually leach out over the period of in case of high heating. So that's also means avoided actually. Then you have this drying chambers. Just in case of the Anderson scale, you have drying chambers where you can maintain your desired temperature, pressure, and air flow rates. Vacuum drying also sometimes the diffusion rate also need to be permitted. Freeze drying, there's sometimes you need freeze drying that to actually retain the nutrient value of the food material. So in case of food, your bioproduct, your drugs, they goes for the freeze drying part actually, because in that case you are not permitted to go the temperature, let's say beyond the room temperature. So if you do the room temperature dry, it may not have perfect drying in that particular. So you go to the freezing part actually in that case. These are some coating preparation techniques. One is the solution casting. This is the most commonly used techniques. Actually, we take our polymer, your pigment, all materials, make a solution of that, apply that. So that is one way. Then one is the actually the spin casting. So the solution casting, you are just pouring actually some material here, entire material on a particular the substrate here, and you can spread that or you can just drop it here. So that is called the solution casting. Spin casting actually you just put a solution on a particular the rotating device and move it at some particular RPM here. So just like this in this, you are dropping the solution at the center and it will spread over the period of time depending on the RPM. You can control thickness. If the RPM too much high, then entire the solution will thrown out actually, and your lot of the material will go waste. So if your RPM is low, so in that case your the solution would get stick to the center only, so you will have the film only at the center. So in this case you have to play with the RPM actually, so to control the thickness. So most of the time in that case at the edges your thickness of the film is high, at the center is low due to the centrifugal force. Another one is the dip casting. This is being used for all mechanical tools actually. So tools you just dip in the solvent just to take out all your the mechanic or your vehicle body parts are being coated by the dip casting actually. So you just dip it in the particular the solution of the paint, color, pigment, primers, and just take out at a particular actually. Now here at what rate you are taking out that control the thickness. If you are taking very slowly, then in that case your bottom of that will have high amount of the solvent. So you will have thicker coating at the bottom. So you have to again take out at a particular speed in order to control the thickness of the film. Now, these are the defects actually. So defects, because if these are due to improper formulation also and improper drying also. So these are some of the defects. There are more than 50 type of the defects in the coating. So these are quite common. Everybody might have seen best example in their household because when they do the painting. This is most common. You might have seen the saponification part. Fading is also there. Some paint which is exposed to the outside environment actually, or some sort of the excessive heating at one of the hand. So one side get faded, other side is you have the good color actually. Just like your cloth, the cloth actually which is directly in the sunlight, which fade over the period of time, which is under the arms actually that have the good color actually. Blistering formation also happens. This happens in case of that if you dry the air coating at a very high airflow rates. So what happens? The top layer becomes dry. In the bottom, you have the solvent, and that happens if you will apply the coat in the winter season actually. So what will happen that you can turn on the fan. So over the few weeks, actually, you will say your coating is dry, but it's not, because you would see that when the hot summer will come, when the temperature would become 30 degree, 40 degree, and there at that particular time you will find this type of the blister formation actually bubbles, because the solvent what were trapped inside now it will vaporize, because now the temperature is high, because the time you have applied the coating that time temperature was 25 degrees Celsius only, now you have 45, 30. So all that solvent will convert into the vapor and it will come out. So how would it come out? It will just form this type of the blisters actually. Sometimes it will come out at the form of the cracks. Now flaking, this is due to improper combinations of the pigments and all this and very highly concentrated one. So in that case, also the solid percentage is too much high. So the sometimes the solvent one layer become dry and you have solvents. So it will not stick. So it will create your flake formations also. It happens also in case of your cooking of food also. If you want mix it properly, you will find a crack that on top your top layer is dry and you will find a crack on that. Just happen in case of milk also, making the cream from the milk. Blooming also, you might have seen this type of thing. This is due to improper formulations of the pigment of top surface. Some pigment bent inside, some is outside. So outside one is providing color, and whatever bent inside that end is you are just finding this type of stuff. Wrinkling also, if you have very high, because the time we buy the paint from the market, earlier time, we used to have a paint powder, actually pigment, we used to use in some of the solvents. And there it is on power base, we have to use the diluent. So diluent people use turpentine oil or maybe some organic solvent or maybe your kerosene, the lighter solvent, actually cheaper one. But it deteriorate the quality of paints. So somehow if you have added more amount of percentage, so you will find that the excess solvent just fall down. So that also creates. So, but these days this problem doesn't happen actually, because that shop owner will always mix you in a bucket. It have a basic materials and then a color. It mix it up, and then you ask you don't add anything into that, because to avoid this wrinkling problem actually. Am I audible? Everything is fine?
Yes, sir. Continue.
Okay, fine, fine. Now, these are some major the research areas in which people are working. People can work about that. So, in case of drying, what you have. So, first part is drying, and drying need a diffusion studies of the within the materials, and then you have modeling and simulation part, because in each and every field, first and foremost part these days is modeling and simulation part. Before going to make it anything on a real scale, modeling and simulation is most important tool these days, because nobody wants to waste the material and time, because it's not the earlier case, perform the practical first and do the modeling simulation and characterize it, check the your batch whether it is good quality or bad. No, it's not. Now these days everything need to be modeled first before going to a real experiment. So we every field, be it anything actually, modeling and simulation part first. You tell what should be the condition, optimum condition, which makes us feasible just to make this particular product. Then what we have in case of films, you have films, you have membranes, you have coatings. So films, these are some classifications, Then in so what studies can be done? So as you can do that, you can coat a film and just take its mass loss. That is the first part. But in case of let's say some heavy material, bulky materials, You cannot weigh the material because that's not handy. How can you weigh the flyover actually? You might have seen all flyovers these days. They will put a metal one and all of them are coated. But you are not supposed to weigh of that how much time will it take for drying. No, you can't do. So that's the gravimetric analysis of that particular type of bulky materials. All your the plant, the materials, plant reactors, your vessels, your distillation column. You are not supposed to weigh that because the weigh is very high and coating material is very low. So you cannot identify anything in that particular case. So in that case, gravimetric study is not allowed. You can do only depth profiling by concentration. You just take some particular point, do the depth profiling at that particular point, and just see how my coating properties are there, composition, and all this. Obviously, optimization. So the optimization need to be done based on the pilot plant experiment being done in the laboratory. You have the model, you have the computer program just to simulate it. You have some experimental data. Now you optimize your formulations, your drying conditions, your compositions, just to get your final finished product as desirable. Okay. Now, this is what I have here. This is a typical example of actually a coating. What you have there, you have a substrate. So I have taken a substrate impermeable, actually. Impermeable, you can have a metal or you can have a glass. But substrate could be permeable, just like your household wall. Your wall is permeable. Solvent can go inside the wall also. And what will happen to that? It will come out because what will happen at that end? Because that then it will be primarily it will go in because wall was dry. After that, as will time will passes on, that need to be dried. So that solvent will have to come out. So too much actually you can say that applying of the moisture on the wall is not allowed. So before coating all the time, you need to dry the wall. Just like in the cement, when you do the plastering is also one sort of the coating. What you do in that case, you add some amount of the moisture only, sir, just to stick your cement or plaster to the wall. You are not putting it 100% dry because in that case, your adhesiveness of the this plaster doesn't come. So you need some amount of the moisture. At the same time, some people just wait it over the period of night, something, what will happen in that case? You will find some sort of bubbles there. That's only because of that, because your material is not getting stuck. So you have to maintain. In case of polymeric film, that the substrate need 100% dried actually. Now, in case of, let's say we have the solvent, we are talking about the example of ternary system. What we have ternary here? We have one polymer and two solvent, or you can have two polymer, one solvent. But this case, we have taken one polymer, two solvent. Actual paint will have more than 100 components. So for the simulation study, actually, you have to quantify that what is the solid material, solid percentage, practically 30 to 40%. The rest of the things are being treated as the solvents. So some may be in a high percentage, base thinner actually. Pigments and all this are being counted as the solid materials actually. So in this case, what we have, one polymer, two solvents. So what will happen in case of chemical engineering point of view? So if you have thing, each solvent will have some the diffusion actually as will apply. So bottom substrate is the impermeable. So the nothing can go to the downside. What will happen over the period of time? Solvent has to go up. So this is the arrow which will say how the solvent is going up to the substrate side. Now on that, if you are not blowing the air on that, what will happen in that case? Your solvent will evaporate automatically into the surrounding air, depending on the moisture content or the humidity inside present. If the humidity present in the air and here both concentrations are same, nothing would get dry. It will remain as it is. So you might have seen in very cold climate, you will say the top surface of paint will always have some water component. But if you want to blow the air on top of that, so in that case, what will happen? This air will take out the moisture, whatever is coming on the surface, and it will keep on continuously means the replacing by fresh air. So in that case, your drying rate would be faster. Now, what will happen in case of very high dry rate? It will remove too much fast that the one condition will come on this top surface. You will not have any moisture here. So you will have purely solid material. So you would think that my film is dried, but it's not, because inside of that you have a lot of amount of the solvent present. So that is also not means allowed actually. So this is from your fixed second law actually, how the solvent concentration will change within this film. The D1 is the means you have your main term, the diffusion coefficient, and D12 is the cross diffusion term only because of solvent 2. So this is your rate of change of concentration of solvent 1, equation 1. Next one is rate of change of concentration of the solvent 2. There is another equation for thickness change, which is not coming in this actually, which you can see here actually. Is it visible now? Yeah, so this is one thing here for thickness of the coating. So how? Because as the solvent is going out, mass of the coating is the decreasing, mass of the solvent, so total mass means over the period of time, this is the mass loss of the solvent 1, this is mass loss of the solvent 2. So mass upon density would give the volume, and volume upon surface area will give the thickness actually. And then if you are calculating per unit time, so you can calculate thickness change of the coating. Now what will happen in that case over the period of time here? So this thickness is keep on decreasing with respect to time. So it is decreasing in this way. So we are just taking assumption that the substrate is large. So in that case, we are not expecting any shrinkage in the lateral side. We are considering only in vertical side only. And these are the flux boundary conditions, how this mass transfer would change. We can provide hot air on top and bottom also. That depend on the what type of the object we have. If we have the movable one, we can provide hot air on top and bottom both. If we are in case of walls or let's say the reactor, we are not allowed to heat from backside because backside is not accessible to us. So we can provide the air on outside only. So we can see these are your boundary conditions actually. So these are flux boundary conditions at the surface 1 and surface 2. Fluxes at the impermeable substrate because mass cannot go in that particular side. So fluxes at the substrate side is 0 only. So these are you have actually two boundary conditions, one on top actually, one on the bottom side actually. So now these are some equations, modern equations actually. This just to calculate the diffusion coefficient in polymeric systems. So these are some modern equations here just to calculate main term that mean the diffusion coefficient D11 or D22, and cross term is D12 and D21. So these are the model. These need the activity coefficient here. So based on activity coefficient and volume fraction of the materials and chemical potential, these model equations are derived. So we have those actually, considering that we want to do only modeling simulation part. So we need all model equation that need to be solved for the equation, because in this we need this what is the D11, how would I calculate it? So I need a modern equation to that, how would I calculate, or this parameter. So the diffusion coefficient cannot be treated constant because initially you will have very high amount of the solvent, and then later on you will have the solvent in 1 to 2%. So the diffusion coefficient is the function of the solvent mass fraction also. So you need the modern equations for that. So once we have modern equations, we need to solve it. So if you can see these equations, these are the coupled partial differential equations, one for the solvent 1, one for solvent 2, other one is for thickness 1. So the thickness 1 is ordinary differential equations, and solvent one is partial difference equation, which are coupled, which cannot solve individually. So you have to think a solution technique. How can I solve these coupled partial difference equations just to have my model predictions? Because in order to optimize mathematically anything, you have to first think solution technique. So we have to think how to solve these PDEs. So in this work, we solved this by Gillikin's finite element method here. So what we have here, you have coupled nonlinear partial differential equations. Now, partial differential equation, you have to think how can we solve, because we are being taught in about the UG courses only just to solve the ODEs by the Rangekutta method, Euler's methods, and all this. So you have to somehow convert them either to ODEs or a system of algebraic equations, because we have the techniques to solve them. So I use the technique finite means element the method here. Here we use the Gillikin's finite element the method. What does it do? It converts them to a coupled nonlinear ordinary differential equations. Now these we have taken now finite elements. You have divided the coating into several elements. Section 1, section 2, section 3. So entire thickness of the coating was divided into several elements. Now it is your choice whether you want element size equal or you want the finer one on top and the coarser one on bottom one. Means if you say in this particular figure, why do you can have you can divide this entire film thickness in the equal element, or you want a very close elements here, the finer one, because as you did the Fick's law. So what does the Fick's law say? Concentration profile drops in this way. So wherever so in bottom case you have because here there is no mass transfer in the bottom, so it will have very high amount of the solvent. So if you will take here very fine element size, the concentration of the solvent is not changing that much rate. What will happen on top side? From here the mass is going out to the coating side, so it is always try to get dried faster. So there would be a huge variation in this particular top segment part here. So here I want the element size which is very small, so that I can capture that steep concentration profile. In bottom side I don't want, because here the variation is not too much, so I want a here bigger particles, means element size. Why would I this? Because each element will give you your several number of the equations. If number of the elements is too much high, you will unnecessarily are getting too many number of the equations, and therefore your computational time will go up. So this is you only that you have to take care that how to control my element size, what elements should I take, because I have to means optimize the computational power of my system also. I cannot say I can give 5 lakh elements and let's run the computer and you will get fed up. Oh, my program is not working, and because nothing is wrong with your program. You have unnecessary exploiting the computational power of your computer. So you have to manage this. So therefore, we have taken here unequal element size, finer one on top and coarser one on the bottom side. Now, once you have this ODEs, then you have to integrate them. So we have actually integrated them with this Gauss quadrature one. That's called numerical integration actually. So this help us just to integrate faster, because otherwise we use the Simpson's 1/3 rule and all this. So in that case, you have to calculate against several points. So in that case, only 3 points will give you the integration which is very close to your analytical answer. So 3 points is more than the sufficient. You can have 4.5 points. So in that case, the answer will not change. Only thing your computational time will go tremendously high. So you have to optimize the number of points also. What points? So it just gives the 3 points. It gives a corresponding weight. Calculate the function at those 3 points, multiply by those weight, add them up, you will get your integration actually. So finally, you will get your ODEs, and that were solved by MATLAB 15. So this we have solved it, and we have published this work in Computers and Chemical Engineering. Once you did a coding actually, so before doing optimization, the important part is first you validate your code, whether it is working properly or not. How do you come to know? You made a program, is working, running, it's okay. I mean, the no error is coming by changing element size, boundary condition. It means you have made a good program. Your programming wise, your program is good. But question is that, is it correct? Is it correct for the problem which you are going to solve? So for that, it needs a validation of your code. So first validation is that if somebody might have solved it, just validate with them, or solve it by hand. Solve it by hand, generate the data for one set of the point, calculate from the program, validate it. So there's a two-way analytical validation, solve it by hand, validate by the program, or test by the someone else. So we did both actually. So we the same modern equation were solved by earlier people. Also we have the also solved, and we have compared it. So from here, this is the graphical way to show it. So graph wise, most of the time we cannot find the variation. How much is the variation? So you have to also calculate data error also, average error also, distance to the mean the deviation also. If that comes less than actually you can say 0.5% something, it means your program is good. If it is more, because graph may you cannot identify that. So this is the validation part of that. Hello?
Yes, sir. Audible.
So if the anyone have any question in between, they can ask in between also, okay? Now, once you did your programming, your validations, your means your program is now working well. You have a good program. Now, what to do actually? So first part is that we have to check what our model is the predicting. So model case we have to measure in case of polymeric coating. We want to measure because the model will give us concentration. Now we want to actually optimize the things here. So before doing on the optimization part, if we can do actually something for our practical, measure the data for that. So we have practical data. We want to validate with this compare with our the experiment. Now we want to optimize the conditions. So that's way. So now this is the technique which will measure the concentration within any thin material. So this is the metal substrate actually here. What you have here, this is the stainless steel. So in that case, you will just pour a polymer solution here, and you will make a film, or you can make a film separately on some substrate actually. From there you can peel off the coating actually. So this is in case of wet coating. So in case of wet coating, you just pour the solution here, put this sample holder on this red plane here. You can see this red plane of the confocal. You can put this holder here, locate the substrate, and then you will find a video there in this confocal actually microscope means the scope. You can identify your pattern there. It means you are the substrate. In that case, first you take the spectra. If it is completely noise, it means you are the substrate. Then make this 1 micron down or 2 micron down, so you are going inside the coating. Get the spectra, you will get the spectra for your dried film. So this can be changed by 1 micron actually, with the precision of 1 micron. So this is a good technique just to measure. Now you can see here, you have some data from blue plane, some from gray plane. This is due to actually mismatch between the refractive index of your film, your gap between the lens and your sample. So this need to be cut because you are the interested only signal from red plane. So for that purpose, you have made a confocal arrangement. Confocal means you have a pinhole here. This is at the focal length of this particular objective. It means only the signal coming from red plane can pass to this pinhole camera, rest will be taken off actually. So that you are getting the spectra from the point where you are focusing your laser beam. Now, what need to be taken care in case of confocal? So each component, we are talking about film here. So we are talking about polystyrene, paraxylene, tetrahydrofuran film. So these are the three systems we have considered. So first thing, you should need the Raman spectra of your constituent. What constituent I have? I have to, these are the, you can say the Raman peaks of this. So it has the several here. One is close to thousands, you have the 4-5 peaks here. 1600 you have peaks, 1000 also you have peak, 1200 also you have peaks, 200 also you have the several peaks. So each component will also, as you can see also here also, in case of the tetrahydrofuran, you have the peaks also. So some of the peaks can overlap. So if you are taking a system where you don't have any the different peak between the two systems, you cannot identify which signal is coming from which particular component. So you have to study first that in case of this confocal part, you have to first list the peaks of component 1, list the peaks of component 2, list the peak of component 3, or maybe n number of components. List all the peaks. Now you have to circle. This peak is not matching with other. It means this system can identify. So same thing we did here. So based on that, what we have found in case of paraxylene, tetrahydrofuran, polystyrene, these are the three peaks: 826, 911, and 1000, which are not present in any other. Means 826 is not present in tetrahydrofuran, is not present in polystyrene. So this is the signature of polystyrene. Same thing for tetrahydrofuran. This is the characteristic peak of tetrahydrofuran in 911, which is not present mean anything. So as you did, many people do actually for color, turbidity of your wastewater. So they put the sample in the photometer, they get the intensity of the that particular UV light. Based on that, you are characterizing how much is the concentration. You are making a calibration curve. Same thing need to be done here. Also, you are taking intensity that you are plotting with respect to concentration there. But here you don't have one component. Here you have several. So you have to take the ratios of the intensity with the ratios of their mass fractions to make the calibration curve. So we did also here. So in case of calibration, here you have three component in case of polystyrene, paraxylene, tetrahydrofuran. So it needs two binary curve, two binary calibration curve. One is for polystyrene tetrahydrofuran, other one is polystyrene paraxylene, because polystyrene is common. So polystyrene is being taken as the reference of the materials, and tetrahydrofuran is as the component which need to be studied from this calibration curve. For this paraxylene, you plotted it, and most of the time you say all calibration comes to the linear, because once we have fixed a combination system, so all your dipole moment, everything is same. Only thing you are increasing your component quantity. Based on that, the signal intensity would also increase. So now you want to test it, whether your calibration curves are correct or not. So you made a calibration curve, you got these line for these calibrations. Now you test some, make for some new samples, test what is coming from this calculation and whatever you have prepared are correct or not. So that's what we did here. We have tested actually with these calibration curve with this for PMMA, in the tetrahydrofuran, PMMA ethyl benzene. Now we have tested. This is the this red mark one is actually these are the three samples which we have prepared in our lab further just to test the calibration curve. This is the column 2 which were calculated from binary calibration curve. So you can see here that there is not much change, 20.67, 20.98. So you can say that whatever is calculated from this binary calibration curve are same what we have prepared. It means now we are confident our calibration curves are proper actually. Once we have all these calibration curve, it means these would be used to calculate your concentration, your Raman spectra actually. Now, you also need the diffusion coefficient. How would you calculate the diffusion coefficient in polymer system? Previously, you got the model. Model gives you D11, D21, and D22. Those are main diffusion terms or cross diffusion. Now, those also need the self diffusion of the solvent. What should be the self diffusion coefficient of solvent 1, solvent 2? So these are being calculated from Brentas and do the free volume theory, which calculate a pre-exponential factor, activation energy, your gas constant, your absolute temperature, your weight fraction of the solvent, and the specific volume of the solvent B11, and jumping coefficient, that how would they jump between when we have in the solution. So you have several molecules. So they jump, they do the van der Waals, the motion, the Brownian, the motion in that. So whichever have the lighter, the molecule would jump faster compared to the heavier one. So you are calculating this zeta 1, 2 here, and free volume. If your molecules are too much packed, they cannot move freely. So that this BFH over gamma is free volume, and gamma is the overlapping factor because you have that much passage. So in this passage, your all molecule has to go up. So what component is free for component 1? What component are free for component 2? Just like that you have one room, one classroom. Classroom is 20 by the 20 in actually the size in the floor area. So it can accommodate some number of people, and that area is means available for all people there present in the classroom. So you have to see what fraction of that is available for student 1, student 2, same thing for component 1, component 2. And then this need to be calculated from this this K11, actually the constant again. So I have marked here some parameters, the 4 ones. These 4 are not pure component. Rest of them are pure component. The property you can calculate from the literature correlations. Rest this D01, zeta 12, K12, and K22. These are not pure component property. Though those need to be optimized from your drying means experiments. Drying experiments, the best way that you just take a solution, check its mass. So mass loss can be taken. Calculate mass calculated from your program and minimize the difference. So that's what we did here. So why do we need to calculate here? So as you will see, the literature says that this is too much variation in these parameters. This is just we are talking about polystyrene toluene system only. Different authors give the different data. One gave the 615 10 to the power minus 4. Other gave 4.8 into 10 to the power minus 4. Other gave 4.17. So 4.18, 4.17 is okay, fine. But one gave 50 into 10 to the power minus 4. Let's say you see the variation. More than actually you can say 50 times. So you have to optimize these parameters for your own system, because this will change what molecular weight of the polymer, what is the polymer chain length. So that you cannot generalize actually. So you cannot take any data from the literature just like that and use it, and then you would be scratching your head. My model predictions are not matching with my experiment. They won't match because some parameters are the system the dependent. You have to optimize from your own experiments. So that need to be taken care in case of modeling simulation work. So this is again the variation that you have. You can see that the variation of a diffusion coefficient 0, you have 5.5 10 to the power minus 3, is very low. As you will keep on adding more amount of the solvent, you see the diffusion coefficient has increased here 10 to the power 9 times at least. Here it was 10 to the power minus 13. Now here you have 10 to the power minus 4. So 10 to the power 9 times diffusion coefficient has been enhanced by amount of the solvent putting into the the solid material or polymer. So that also need to be taken care. So those only can be, means these parameters need to be optimized from your drawing experiment. So what drawing experiment? In case of the optimization of the parameters, we have to always take care actually the simplest possible experiment for optimization purpose. No need to go for complicated part because complication also will have some error. Okay, so they just take base material, what basic experiment can be done. So what we did here, basic, I mean the experiment here, we have taken a film and just pour on the sample holder, put it on the micro bearing balance, and just take its weight with respect to time. Easiest possible way. Chances of the error are very low in that because we are not doing anything in that. We are just making the mass. So these days you can have a computerized the bearing balance which can automatically record the data over the entire period of time. So manual errors also went away. So now same thing you also calculate from your program. Now you minimize the difference between the two by taking those parameters, those four parameters. So you have those four parameters, and since you have four parameters, more than 1,000 combinations, more than million combinations can minimize the difference. More than millions if you have more than one parameters. Because you are just combination. If one you have decrease, other you can the increase. So any combination can work. So any number of combination can give you this type of graph. So how do you make sure what is correct? So for that case, you have to do the literature survey for that. Find the brackets. This will change from here to here. Okay, this range will change from here to here only. So I have to optimize this particular parameter in this range, parameter 2 in this range, parameter 3 in this range. Just like the overlapping factor cannot be more than 1. So if you are value are giving 1.2, it means you are wrong. So you are putting a lower bound and a upper bound for each and every parameters. In combination of that also you will get several combinations. So there you are actually not in position to control further actually. So if your bounds are fixed, then you have to take those combinations, and there could be many combinations. So luckily you may get one combination. What you will do now, you actually try to fix one parameter, optimize 3. So that's need to be regression analysis again and again. So this is, you can say, one of the optimization we do, and everybody who do computation work, they also do it. So these are the optimized parameters for this system here, PMMA ethyl benzene system. So what we did, what is the objective function here? Objective function is the difference between your model predicted and experimental one, calculated on each data point, and just add them. Absolute actually, don't do plus minus, just add all of them. You are minimizing the difference only, total sum. And the time it will come to means practically it should come 0. But in computational work, it never comes up actually. So it can be a minimum. So you have to give a, what should be your minimum value, 10 to the power minus 4, minus 5, minus 3, something. And that data need to be considered as an optimum point actually. Same thing we did for PMMA THF system. So we got these for optimized parameters. Same thing for polystyrene tetrahydrofuran we did. And then we did for polystyrene paraxylene. So you will have several combinations for each system there, because once your code is everything is working and your optimization code is fine, you are very good in starting gas value. So your code will converge. So optimization is always a gas dependent. And you don't know what gas should I give. So sometimes it doesn't convert, it doesn't give the answer in one trial. So you have to give several number of trials just to get one optimized data point. It might be possible that you have to spend 1 week, sometime maybe 1 month, depend, because you have here more than actually 4 parameters more than one parameter, so you cannot go. So it need lot of trials. So it is very time consuming part. So that is optimization is always a time consuming and a tedious job. So somehow we have to find the easiest part. We did for that. We will come to for that part actually. Now, once we did optimization part, now we have to see that out of these four parameters, which one is the most sensitive parameter? I have four. So if I change for plus minus 10%, each parameter I will change now one by one. If one parameter cannot change my prediction significantly, so I should not bother that parameter. I just keep that parameter as a constant. I should focus on others on which slight change in that there are huge change in the prediction. So I will very precisely focus on those parameters because those are most tedious ones. Just changing in point value, my prediction is going completely out, just like this. So if you are changing this zeta 13 by plus minus 5% here, so this is my optimized one. So if I just changing one, there's a huge change here in the prediction, just 5% change. And my experimental data is the somewhere here. This was my first optimized set with the black star one, first optimized set. And you see once I was comparing with the experiment, it is not able to predict. So something went wrong. So I have to re-optimize because my combinations are four. So I have to see the sensitivity. What good can I do for this one? Same thing for this. In this case, if you see, if I change 5% plus minus 5%, for in case of highly volatile, the solvent one, nothing is getting changed. So for highly volatile one, nothing is getting changed. So for this parameter doesn't matter. But for low volatile one, paraxylene one, it is most significant parameters. So I have to take care for that. Same thing for this zeta 1, 2, 3. That this is the again. So in this case, what we have found with this all optimization work, drawing simulation part, in case of ternary system, what we found that this actually your interaction parameters are not the significant for highly volatile one, but they are most significant for low volatile components. So a lot of care need to be taken care just to optimize this parameter. And this work we have the published in Journal of the Applied the Polymer Science. Now this is what once we have done the optimization part, now we want to predict our model predictions and with drying experiments. So we did the depth profiling. Here we are comparing the model, which model is good, because previously we have seen 4 models, but there are 4 or 5 more because they have put some constraint because some cannot measure the diffusion coefficient properly or the activity coefficient properly. So they have correlations. So some simplifications, some have come to a very dilute coefficient, as you might have seen in thermodynamics. We have taken gamma infinite dilution activity coefficient or dilute system. You got a very simplified correlations that easy for calculation, but it doesn't mean that it will give you the correct answer. So we are comparing various models here. So what we found here, the model of Zielinski-Hanley and generalized model and case one of Elsoy and the Duda are close to experiment, but none of the model is able to predict entire drying behavior of the coating. You see the primarily in the beginning of first 500 seconds, every model is predicting well. Now at the end of the 500 seconds, because what happened at the end of the 500 second here, your top layer have very low percentage of the solvent, bottom layer would have high percentage. So all your models are actually over predicting the data. Experimental values are the lower than the model predicted one. So your model, something needs to be done in that particular case, or you need to do the simulation in 2 parts. One is part 1, one is in part 2. So same parameters will not serve the purpose for entire drying behavior or entire course of the drying. In case of high diffusion one, all of them are good. All models are good. even if at the later stage of the drying, all models are under predicting your concentration profile. In case of low volatile one, your models are over predicting. In case of high volatile one, your models are under predicting. But all these changes are there only at later stage of the drying. So these may be due to some change of diffusion characteristic from rubbery polymer from Fickian to it might have gone to the non-Fickian the behavior. Elasticity of the solution might have come, viscoelasticity might have come into the picture actually. Now this is for the another system. The same predictions we got for another system also for PMMA tetrahydroethyl benzene. So what we were guessing for previous systems, same thing was valid here also. So this work we have published in Journal of the Applied Polymer Science. Now, based on this previous part, actually what we did, we measured the concentration profile by confocal the Raman spectroscope. Binary calibration curve also we have tested that those can be used in case of the depth profiling. And diffusion theory, whatever models we have tested them, and none of the models were predicting that. So a lot of scope is there to develop the new model actually. Now, once we did for that part, now we did the modeling, simulation, validations. Now we want to optimize the drying product. Means once we have the film, we want to actually optimize our drying condition. What conditions should I dry? Everything is fine? Anyone have any doubts or anything is, am I going faster or means is it fine?
It's fine, sir.
Okay. So what you have here, once you will apply, make a film. So film in industrial scale need to be dried in some dryers. So this you can say a typical dryer. On this film is moving on some web. Web means it is moving and the rollers actually. And it moves at some RPM. So what you have here, so at this part you are getting a wet film. At this end you are getting a dried film here actually. In between of that, you have a dryer. In dryer, what you are maintaining? You are maintaining a drying conditions. So you have now two choice. One, you can make just like in case of home painting, we don't do anything. So everything is drying at same airflow, same temperature. But industry, the scale, we have the option at that particular place. So entire length of the dryer can be dried at different conditions. Let's say primarily you have very high amount of the solvent. So you can dry maybe a very high temperature, very high airflow rate because nothing would happen in that case. Just like when we cook the food, primarily we put a lot of the water and all this and we can cook the food at a very high flame. Nothing would happen at that end. What will happen at the later stage of the drying? We just tune down the flame because we don't want to burn it. Same thing can happen in case of these coatings also or drying of any product also. When we have high moisture in the beginning, you can give high temperature, high airflow rate because it will help you just take out maximum amount of the moisture. Later on, you have to control your temperature and airflow rate because same amount of heating or energy supplied cannot be given because it will burn your product or means your product quality will change. So this is the typical example of three zones. We have divided this particular dryer in three zones, zone 1, zone 2, zone 3. And each of the case you have three variables. One is airflow on top and bottom. Other one is the temperature. Temperature in a particular zone is fixed. Now, what can have airflow on top and bottom? You have two choices. Either you can have same, or you can have the different airflow on top, different airflow on the bottom, and temperature. And second thing, how long should I dry in zone 1? The time also. So each zone I have three parameters that need to be optimized. If I go to the zone 2, I will get three more parameters. Zone 3, I will get three more parameters. So whoever are working in optimization field and all this, they will come to know we need to optimize one parameter is very tedious job, very tedious. And you have more than one, three, or you can imagine your the difficulty would become almost the square of the number of the variables. So you will have 9 times the difficulty in zone one, then again three and again three. So difficulty level is going increase where you want to optimize more and more parameters. So what we did here, so we have a drawing program which we have made in the previous part, and here we are optimizing for binary coating, actually one polymer, one solvent, because here it's easy to optimize compared to directly going for ternary system. So in this case, there we have previously temperature variation, heat transfer, the variation there. So what we did here, let's say we have changed the temperature based on the solvent boiling point. We can give the any temperature which is lower than the boiling point of the solvent, because we don't want to boil it. So if you can give a very low temperature, just like a atmosphere, so this is actually here a temperature of 75 degrees Celsius in case of toluene. So what we found here, uh, initially in entire film you have concentration is same, the nearly 0.678, 0.65 here. So you can see the black line. At T equal to 0, your concentration is same throughout the entire film. As the time will pass on, your concentration at top would decrease, because from top the solvent is going out. Okay, so this you can see the change in top concentration is this much, very high change, 0.6 here, and top is this is nearly to 0.45. So how can we capture it? Here is no change. So as you say, as I told you previously, that we want to have unequal element size. So suppose we have taken equal number of the element. So we are just having more computational time in this particular zone, where in bottom side there is no variation in concentration. So I am wasting my computational power. So I just that need to be taken care. Now you say at 40 seconds, concentration is drastically changing, and let's say at the end of the 100 seconds, you find at top surface the concentration is not changing much. Concentration just a change in thickness, let's say is changing very huge value. Here is concentration at the 0, here you have very high significant value. So if I say here the element size is bigger, so I will miss this particular picture here. I cannot able to capture it. So in this particular section, nearly top surface, I need more and more amount of the element so that I can capture the steep concentration profile. And bottom side, I just want a bigger one, because here no change, not a huge change here. So this is slowly changing. And let's see how would the residual solvent in the coating and its coating temperature, because I need a coating temperature also. My coating should not boil. This is my constraint, or let's say my constraint on the optimization, that any time during the course of drying, my coating temperature should not exceed the bubble point temperature of the solvent or coating. So here, if I plot the bubble point temperature, the blue one, coating temperature is the pink one. So you say that the huge gap between bubble point and coating, it means I am safe. My coating is good quality because it's not boiling. But what about the other end? Other end, if you will see that the solvent here, I have this much high solvent here. Nearly, you have here one here. Nearly 10% solvent I have. So this much solvent is getting retained in my coating. So I have two losses. One loss is that my solvent is going waste. Second loss is that whenever the temperature will go high, this solvent will boil and it will form the blisters in the coating. So I will lose at two ends. One is at the solvent end, one is at the quality of my product. So I can heat up at the high temperature. What will happen at the high temperature? This is what I did. I just changed the temperature to 120 degrees Celsius. Rest of the parameters are same. what I'm finding here, that within 5 seconds or let's say within 30 seconds, my coating is getting dried here. Coating is getting dried, the steep concentration profile, everything has been dried. But what about this coating temperature here? Let's see the coating temperature. It's approaching the bubble point. My coating is about to boil. It means I am able to minimize the drying time. I can minimize the drying time, but my product is highly susceptible to get failed only because of the boiling of the solvent. So I have to give a temperature or heat transfer in a range. Okay, my coating should not boil also. At the same time, it should take less time for drying also. So that needs optimization of your temperature, your airflow rate, and drying time, zone temperature. How long would I dry? So in between of the previous one, there's a mild condition where you are drying at a low heat transfer rate. Here you have a high. In between of the two, you will have some optimum conditions which can optimize my drying condition and the solvent and drying time. So for that, we have made a objective
Excuse me,
function because in
sir.
case of the optimize, yes,
Uh, in the previous graph, the first one, how did you come with 75 degrees from the starting? Why not 50, 60, or 40?
yeah, you can go ahead actually. So this is actually what you can say in case of toluene. If you are talking about the toluene, its boiling point is how much? Nearly 110.
Yes, sir.
Nearly 110. So if you will take you can take that, mean the example of 50 also. 50 will take further more time. 50 will take further more time just to reach at a steep concentration profile or let's say nearly zero concentration on top. You can take it 50. So once you have this is just to show that what will happen if you will dry at this temperature. What will happen in case if you will dry a temperature close to the boiling point of the pure solvent. So this is just a pictorial example. There are no hard and fast rule just to take 50 or 70. You can take
Okay.
50 also. Okay.
Mm, okay, sir.
Yeah. So now, in case of the optimization, you always need a objective function. What do you want to minimize? So objective functions are for two types, either the minimization of the something or maximization of the something. In our case, we are the minimizing the solvent. So our function is the objective function is the minimization of total solvent retained in the coating actually. So once you have the solvent concentration, if you can multiply by the thickness, so you will get the concentration per unit mass per unit area, right? So that is also a mass. So in this case, this is our means the objective function. So concentration we have calculated from our the model predictions. Thickness also we know. So we at every time just do this the product and calculate the total. And for every temperature conditions, every heat transfer. So you just keep on doing that. Now these are the some range of heat transfer. These are the maximum practical possible range. So you know the what is the range my heat transfer coefficient, or you can say practically your airflow rate. So airflow, the forced convection heat transfer. So if you don't flow the airflow just like in the room temperature without fan and all this, your heat transfer coefficient would be 8.36 watt per meter square per degree Celsius actually. This is your heat transfer coefficient in natural convection mode. If you will want to have an excessive high airflow, this is the maximum possible, 1.2 into 10 to the power 5. You cannot get a heat transfer coefficient in case of polymer film higher than this. So your heat transfer bracket, heat transfer coefficient bracket is now fixed. You can change your heat transfer value in this particular time. You have to also take a pressure. What should be the pressure in my chamber? So let's say you want to dry in atmospheric conditions. So your atmospheric temperature is 1 atmosphere. Based on that, you can calculate your bubble point of your coating, not of solvent. Coating bubble point would be the different as compared to the solvent. Actually, pure solvent would have the different one. So these are your constraints, and based on that, bubble point would be calculated. This is your constant that all time I am calculating bubble point. T bubble point of coating and should be always less than equal to the boiling point of the coating actually. Now what we did says once we optimize it here, once we have a good core testing already we did, everything we did, now we can play with our parameters. Our parameters are what? Our time. So let's say primarily you have fixed a time. I want to optimize my conditions of heat transfer. Fixing the time. Time I have fixed is for this. Uh, let's say you have fixed a time, let's say 100 second or 120 second. You have fixed a time. Now you are just playing with heat transfer. You have two heat transfer. One is on top, one is on bottom. So you can make the several combinations of that. Keep on finding the optimized value for each combinations. It will not come in one trial. You just give a heat transfer coefficient guess, run it, you will get a one value. Another side, you run it, you will get the another value. So you are getting for each temperature you are getting one value. At 110, you got one value of the bottom, one value of top. So currently you say both are same. Then you change the temperature to 115. So these are, you can say, the means optimized heat transfer coefficients at various temperatures for a given time. For this case, time was 120 seconds only. Now what I am getting here, in this case, if I see in this particular temperature range, the objective function is residual solvent. So if I see the curve of the residual solvent, initially it was high, then it went down, and this is the point it came to the lowest one. After that, it is again further increasing. It means I have several local optimum values of the residual solvent and corresponding heat transfer coefficient, but I have only one global optimum, which is this actually, nearly at 108, 16 degrees Celsius something. For that, this is my corresponding top side heat transfer coefficient. This is my corresponding bottom side heat transfer coefficient. So you got previously local optimum, now you got a global optimum. So whenever we do the optimization program, most of the time we get confused that we got the optimum point, and now we are telling, now I got an optimum value. No, you are not. You are only at local optimum value. Maybe luckily in first trial you may get a global optimum, but you need to check. You need to check by changing those values further. So for that, you have to draw the graph of this way. Based on that, wherever the least one, that is called your global optimum. So that need to be considered as a global optimum value, your final optimum one. Fine. So based on that, what we did here, so this, as I talked in previous one, you have more parameters, you have three parameters, your time consuming part, tedious job. Somehow we have to minimize this computational time or this complication. So what we have come up here, that first what we did here, that just make the coating temperature equal to the bubble point, because that is the maximum possible temperature you will have. Now we know the range of heat transfer coefficient. So what we did here, initially you can give the heat transfer coefficient in this given the range, actually a 1.5 in 10 to the power 2 and 8.36. So you have these two ranges. You can give any value of that. In the safer side, you can give either same on top and the bottom. Based on that, it will optimize your heat transfer coefficient, and it will give you some optimized heat transfer coefficient values. Fine. After that, you just note down the corresponding residual solvent. Now, change your heat transfer coefficient by step 2. Add the total. If total is greater than 1.5 in 10 to the power 2, then adjust the top and heat transfer by this formulation. Top you make sum minus bottom one, and bottom you are providing the highest one. If it is the less than 1.5 in 10 to the power 2, then adjust your heat transfer coefficient. Top side is 8.36. and bottom side is the sum minus of top one. Just do this. So here you are not using now the optimization code because that is time consuming part. Here you are using just a normal code, and in that you are adjusting your heat transfer coefficient by this simple formulation. And now you say that between 2-3 tiles you will get the optimum values. We did that actually. So this is the before that why we have to give the bottom side heat transfer coefficient always higher, because in bottom side what we did maximum because your the substrate is the impermeable, so the bottom would always have high amount of the solvent. So for that, if you will provide more amount of heat, it will convert it into the vapor, and diffusion coefficient would be high, so that it's the solvent will the diffuse within the coating, it will reach to the top surface. So in that case, backside heating is favorable. The more amount of the solvent from bottom will reach to the top. By chance you have top side heat transfer coefficient is high. So you see here, once the top side heat transfer coefficient is high, your drying rate is high. Your drying means solvent, the removal rate is high in the beginning, because in the beginning entire coating have same amount of the solvent. So initially is high. What will happen over the period of time? Top surface will decrease in the solvent. So your drying rate is keep on the decreasing and the decreasing. Now, whatever in case of low topside heat transfer coefficient, you see that this is the drying rate. It's not as much high as for the high topside heat transfer coefficient, because if you will just blow the air at a very low rate, your drying would be slow. But it will dry for a longer period of time. So if you say area under the curve, for red curve and blue curve, so blue curve will have a high area under the curve, means high amount of solvent has been taken out as compared to the red one. So therefore, we always go for low topside heat transfer coefficient. And whenever we also cook the food, have you seen the cooking of food? All on the time, cooking of anything is do by backside heating. We are heating from bottom. We are not heating from top. Because if you will provide heat from top, your top material will be cooked. What about bottom? Bottom is the impermeable, the substrate, your pan of the container. Nothing would happen here. It won't cook. So over the period of time, your top layer would be cooked, and below that you will have uncooked the material. That is also one of the example of backside heating. So same thing is being done in case of polymer films also. So this is what we did for, and this is also validated by one of our group member, Khandelwal. They also published that whenever you have top side heat transfer is low as compared to the bottom side, your coating will always retain less amount of the solvent. So what we did here, we made this code, and now this code will remove the need of your optimization program. It won't need now the optimization program anymore. It will just need a simple MATLAB program or any program, change the value by this, note the corresponding amount of the solvent. What we did here. This is what we did for each temperature for a single zone. We optimized we found the residual solvent and heat transfer coefficient for top and bottom. We are comparing by the method which we have proposed. We just need a object, means just a program. One by rigorous optimization program, which we did the nonlinear least square fitting and all this. We compare the two, and we see the calculated value by us and by the normal optimization code are almost same. You see here 150.48, 150.48, and again for this also, and the residual solvent calculation is also same by both the methods. So here you will have is just slight change here, 96.14 at 120 degrees Celsius, 97.56. So we are, you can say from this code, we are always very close to the optimized values. But what great we did in this, we have just minimized our computational time, our gas dependency also. So we can just start in anything and within 2 trials, within 3 trials, you will get your optimum value, close to optimum value. Okay. So this scheme we have published, and this is what once we have tested for single zone dryer, now we go for multi zone dryers, the 3 zone also. Now 3 zone, as I was talking, for each zone you have 3 parameters: a time, a heat transfer coefficient. So you have to manage the two. So what we have found here, if you will see the last column, if you see the last column, your heat transfer coefficient, residual solvent here, the 7.82. When you have first zone is 5 seconds. And then if you have first zone is 10 seconds, you have the 6.5. Then the 20 seconds, then 30 seconds. So what you can compare from here, when your zone length is too low, you have high heat transfer coefficient. When high amount of the residual solvent, when zone length is further high, you have again further high heat transfer coefficient. So neither too short, neither too long are permitted. If you have a moderate, let's say you are 10 seconds, you are getting a minimum amount of residual solvent. But there is no hard and fast formula just to calculate what time should I give. We have just concluded one thing: it should be reasonably long, neither too short, neither too long. But for all your program, all your case study, you have to find your own. You cannot generalize it actually. So total drying time actually here, if you will see, uh, here you can calculate for 5. So total drying time here, if you will calculate here, so is total 5 plus 5 is 10 plus 5. Total drying time was the 60 second. 60 second was divided into several combinations with a gap of 5 seconds. And we have found optimum found that first zone was 10, second zone was 30, and third zone is 20. So second zone is always reasonably long as compared to zone 1 and zone 2. Okay. And you see in zone 1, your heat transfer coefficient is always higher than zone 2, because at that the beginning you have more amount of the solvent present, so you can provide more heat in the beginning. Later on you just keep on the minimize your heat supply to the material. Obviously you have to give a longer time, just like a cooking of food. When we goes a concentrated food, the material, we just slows down a flame, cook it over a long period of time, your quality of product, quality of taste would be different. Here same thing happen in case of coating soup also, because in polymers, when concentration of polymer becomes 70% of polymer, diffusion rate decreases extremely low actually, extremely low, 10 to the power minus 13. So for that, your drying on top should also be in that order of the magnitude, must also be decreased. Otherwise, you are providing heat to the polymer, solvent is not present. So what will it will burn your polymer or film. So as you see here, this is the bubble point, that temperature, objective function. These were the constant, the coating temperature and bubble point temperature. So these are not touching actually, these are just close. So here the values are very close. So therefore you can say these are the overlapping. It's not actually. So if you zoom them, they are have nearly 1 degree gap here actually. So therefore we can say we are nearly close to the boiling point, but we are not at boiling point. Why boiling point? Because we want to take out maximum amount of the solvent there. Close to that, not at that particular range. So based on that, we did for 4 zone the dryer also, same technique, same method. We did for 4 zone. And finally, we did for the bubble point temperature for the 4 zone also. Same conclusion were valid also in this also, that your first zone should be not too short, not too long. Second zone is always higher one, and each subsequent zone was lower one. So in that case, you are finding equal here, 20-second and 20-second. Okay. Second zone is bigger actually, 30-second compared to all other zones. So this again copper means the temperature of the coating and the bubble point, and this is the amount of the residual solvent. So this was at the end of the zone 1, then zone 2, zone 3 and zone 4, and finally we have minimized the residual solvent. Sorry. So with this optimization study, we came to know optimum heat transfer coefficient decreases as we raise the coating temperature. How much can we raise the coating temperature? The maximum is just 1 degree or 2 degree lower than bubble point. That is the constraint for the coating temperature. It will minimize your heat transfer coefficient rates. Top side coefficient is always lower as compared to the bottom point, just to provide a back heating and to take out more amount of the solvent, just to keep the solvent in a diffusion mode in entire film. Therefore, back heating was always permitted. With the help of that, by maintaining backside heat transfer coefficient always higher than top side one. If you have high top side one, top layer will dry it faster, it will become pure polymer. You will have lot of amount of solvent present in the film, which is not allowed. Overall heat transfer coefficient are always higher with lower air flows on top. If top side is low, so overall heat transfer rate, the area under the curve is always higher. It means you are taking more amount of the solvent. Sizing of first zone is always critical. So it should not be too long or too short. So it should be reasonable actually. So in all previous case, you got 10 seconds, wherever the drying time was total 60 seconds only. So 10 seconds, you got 60 seconds, you can say the 6% of that. 6 or how much? 10 by 60 is nearly 30% of that. So you have that, and subsequent zones are flexible. They can be equal. Second zone is also large actually as compared to the last other zone, zone 3 and 4. And this work we have the published in industrial engineering chemistry and the research actually. And with this actually I want to acknowledge my various teachers, my primary teachers, Satar Ahmed ji, Suraj Singh, my B.Tech teacher, Dr. O.P. Rama, master's guide, Dr. Bhaskar Bar, Ph.D. guide, Professor Madhubin Jamur, my colleague, Dr. Avinash Chandra, and my colleague, Dr. Shekhar Agnihotri. My B.Tech student did a lot of work actually. Chitesh Bhargav, Sakshi Shukla, Kshitij Tiwari, Udit Mohan Singhal, Rahul Dikshit. M.Tech student Jitin Kadaria and Aman Patania, Anubhav Prasar. MSc student Deji Sharma, Harleen Ishita Sharma. PhD student Jyoti Sharma and the Devyani Thapliyal. DST for providing funding for this current work, which we are the working in polymer solvent coating. And with this, thank you for your kind attention listening to this entire presentation. Any
Okay,
question?
thank you very much, sir, for your nice presentation. And I hope that there are some queries. So please go ahead. If you have any queries, please go ahead.
Hello, sir.
Yeah.
Yeah, this optimization can it be applied for other processes as well?
Optimization, the technique which we have found that just take heat transfer coefficient, minimize that way, that thing, you want to ask that thing? Or the program code which we have made, or you want to apply for any other
Yes, sir.
process, just like
Yeah,
the
the basic
adsorption?
approach.
Yeah.
The basic
Basic?
approach.
Yeah, that's fixed for same actually. Basic the approach for means the optimization is same. First, you need a code. You have to make a program. That program first need to be checked. So you have to do the validation. The best one is that if you can solve it by hand is okay, well and good. Other way that if the somebody has already published that type of computational work, so just check your code with them. The whatever take the same boundary conditions what they have done. Take and test it because the validation of the program is must. Without the validation, you cannot trust on your data.
Okay, sir. Thank you, sir. Nice work, sir.
Or actually in case of because you say the all of the computational work may not be published. In case the data are not published, you are not getting the data. So in that case, what can you do? You can just perform a simple experiment. Simple means easy to perform. Don't go for high-end one because more of the high-end one, there are two reasons. First, you cannot get that high-end facility easily also, and slight change in the measurement can give you the huge the difference. So simply weighing or just UV photometer, you can get some concentration, something. Go for that only and validate your experiment with that. So you can check with that way also.
Okay. Uh,
Sir, what is the effect of air velocity and humidity on heat transfer coefficient?
See, air velocity and these temperature is everything is clubbed will give you the heat transfer only because airflow rate will give the force convection only. So airflow is indirectly your heat transfer coefficient actually. So you will have Chiltern and Coleman analogy. So there you will put your air velocity and all this Prandtl number there, and based on that you are calculating your heat transfer coefficient there. So air velocity would be clubbed in the heat transfer coefficient. Humidity actually will control the evaporation of the solvent actually that from top surface to the surrounding air. So that you need the partial pressure of the solvent minus partial pressure of your vapors present in the air actually. So if that the difference is not too much high, your drying would become extremely slow. And most of the time the solvent is same, vapor pressure at outside and inside are same. Then there practically would be no drying actually.
Yes, sir. What did
So
you
the
use to do
humidity
your experiments? Air or any other gas?
in this work we have taken pure air actually because we say that air is not getting the reacted with our polymer the material. If the sometime if your polymer the material is getting mean the affected, so you have to take the inert material. Most of the time people may use the nitrogen also in that case, nitrogen gas also, because air will have the component of the oxygen. So if your product is getting oxidized in case of that temperature range or heating range, you are not supposed to use the air actually.
Yes. Thank you, sir.
Good
Yeah,
afternoon,
welcome.
sir.
Yeah, good afternoon.
I have a query, just very basic. Like we are also using that substrate, metal substrate
Okay.
that you have shown, and the system is polystyrene paraxylene. Initially,
Hmm.
when we performed that experiment during the winter session, so
Yeah.
one or two coatings were able to remove. They were able to remove from the metal substrate. But later
You
on,
want to make the you can peel off easily
yes,
from the substrate, right?
yes. Initially,
Okay.
it was easily peel off, but after some time, it got
Uh,
stick to the substrate. And I have done everything: oven drying, desiccator drying, everything, and it is not. I'm not able to peel it off. Is it a problem with substrate or something, or what can we
Actually,
do?
yeah, it is because once your the substrate is actually smooth.
Yes,
Smooth means once you will do the machining of the substrate, you will get some baby type of characteristics. as I can show you actually. So this is there in the beginning. So I can show you this one. So you can see this actually substrate. You can see there are the fine lines here.
Yes, sir.
So in the beginning, actually, or maybe the time you clean it, actually the time you do the washing and cleaning. So in that case, if you have just cleaned it with very rough solvent means, let's say tetrahydrofuran. So
Okay.
tetrahydrofuran is the rough solvent actually.
Okay.
So in that case, it will give very good means you can say etching resistance to this. And after that, if you will apply the film, it will get stick to the, it won't come out that much
Okay.
easily.
Okay. Okay.
Now, depend on polymer also. If your polymer is of, let's say, highly glassy one, just like polystyrene, is the glassy
Yes.
polymer, as compared to the PMMA.
Mm-hmm.
So PMMA film will not come out easily as compared to the polystyrene, because polystyrene is some brittle in the character. Once it is dry, it can easily peel out.
Mm-hmm.
Second part is that the time you are pouring the solvent into this particular mold,
Okay.
in that particular by chance, if it is getting filled and getting attached to the edges of the container,
Mm.
it's actually is strength, or you can say contact in the metal surface increases actually.
Okay.
So that also the impart the stickiness to the substrate actually.
Okay. So
So these things
the
need to be
solution
taken
is
care of. Solution is that is as compared to the stainless steel, the material, once you wash it after the washing it, you can have a washing with some light solvent, just like paraxylene something, and then dry it actually.
okay. And one more question, sir.
Yeah.
If we prepare some solution like and it become homogeneous, okay,
Okay.
then we have to prove that the solution is homogeneous. We write that we prepared something. Somebody asked like, how did you do?
How do
And
how do you want to make sure that the solution is the homogeneous or not?
yes, so we can
Okay.
provide the pictures and all, but is it ethical,
No,
like
no.
according to research and all?
Practically, also you can do it actually. You can take the micropipette
Okay,
and take the solution there and fill it in your cubit, which is
okay,
you use for UV photometer, right?
okay, okay,
UV photometer you do. So you just dip it to a particular depth, take the solution from the there, take your the UV spectra, so you will
okay,
get an intensity peak. Now
okay,
you dip it at the different depth, take it another spectra there. So if your intensity of the signal is not changing, it means your composition is the homogeneous in that. But that is one of the way.
okay, okay,
Okay.
okay, sir. Thank you so much.
So that is one of the way. Other way that if you have the access of this confocal, so pour the solution, put it there, and just take the Raman the spectra on as early as possible, because it will immediately will get dried. Or you
Yes.
just put it in a closed container, glass cubit, take it there. So if your intensity is not changing, you are the homogeneous actually.
Okay, 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 okay. Thank you so much, sir.
Yeah, welcome. Any other question?
Is there any other question? Okay, so if not, then sir,
So okay,
actually
yeah, yes,
I
sir.
have some questions. The two questions.
Okay,
One that meaning you have performed some kind of simulation part for your this study, current study.
right.
So is there any software you have used, or you have used the kind of code, prepared the code
Yeah,
and based on that?
No. Actually, I did all programming, all computational work on MATLAB.
Okay, on MATLAB. Okay.
Uh-huh.
Okay.
Yeah, I and moreover, what work I have shown that all of this has been published.
Okay.
All MATLAB codes are available on those papers.
Okay.
So you can, all those papers were full detail with full program actually. So I have provided everything so that anyone can use them.
Okay, sir. Thank you. And next question I have, like you have given some kind of brief about the thin film coating. So
Yeah.
in the thin film coating, sir, is there any requirement that if suppose we need to, because of coating, basically the basic purpose of the coating is to remove the air, and in that,
Remove the air. Yeah. It's
okay,
actually one of the purpose. Remove the air is one of the purpose. Sometimes we want to impart a mechanical property. Sometimes we want optical property. Sometimes we want a particular color.
okay,
Sometimes we want means the anti-corrosion, the property. Sometimes we want to make a stack of the layer just to separate the several things, just like a polymeric membrane. So in case of the selective separation, you have one layer of the different material, different porosity, and another layer of the different porosity. So one membrane can do the separation of the so many components, just like your the chromatograph, gas
okay,
chromatograph you
uh,
have the different beds. So each bed give you the different product, right?
okay,
So same thing in case of polymer. So you can purpose are the several. One is the protective. In that case, you just want to take out the air. One is functional property. You want to impart electrical property or magnetic
mechanical power.
property, magnetic tapes and all the storage property, just like the data capturing electronics purpose. So
Yes,
depending on need, you have to.
okay. So, sir, my question into that is there what is the importance? Suppose we want to find out the interaction between the thin film coating which we want to coat onto some particular surface. So, suppose we want to find out the interaction between the coating and the surface. So, is there any kind of a proper methodology or the way which from which we can do it?
Yeah, you have actually. So if you want interaction in terms of bonding or the strength, that how rigid it is
Rigid
and
they are, yes.
how can it be peel out. So you have uh, actually peeling of mean the instrument. So you can put a press on the film, means just like a vacuum pump,
Hmm.
stick to the film and just try to take it out. So you have to a peeling force, that how much
Okay,
force you want to put it just to peel it
put it.
off.
Hmm.
So those instruments are there actually. So you can just take that also,
Okay,
and that way you can say that how because you see this Teflon coating on your cooking wares, they
hmm.
cannot come out so easily. So you can put the etching resistance, etching power to that, so that they can get stick and they will not come out at a temperature to 500 degrees Celsius and more also.
Okay, sir. Okay, okay.
So that can be done.
Okay, sir. So, if not any other queries, so let's thanks our
So
yes, sir.
yeah. Before that, actually, we will end it. That I want to share with this audience actually
Okay,
that we are conducting a short-term course on at NIT Jalandhar actually for computational methods and analysis for the engineers for 18th to the 22nd next month. So interested participant can join for this actually. Uh, and these are the experts that the Professor Guri from IIT Bombay, Professor Tanmay Basak, Professor Senthil Murugan, Gaurav Mane, Seshagiri Rao from NIT Baranga, Ashish Chaurasia, Bimal Kumar, and from ABB also we have. And these people will talk on various aspects, linear, the regression analysis, finite element, the modeling, multi-physics console, RSM actually data analytics, orthogonal calculation for PDEs for the adsorption, then the modeling of the membrane processes and polynomial interpolation and the least square approximations, molecular modeling and simulations, and formulation of finite high difference in heat transfer case, and modeling simulation of wastewater. So this is one of the short-term course we are conducting in the next month. And in the December, we are conducting another course on current and future scope of the surface coatings. And there we have the expert from Greece, USA, from the 3M corporations, East Michigan University, and Hydromers in the USA, and Jindal Polyfilm actually, and the Asian Paint and Tata Motors. These will talk about fundamentals of coating processes, architectural coating, glassy coatings, polyurethane coating, smart nano coatings, polyurethane coatings, sustainable coatings, flexible and packaging film, nanomaterial, and antimicrobial coatings. So these days, this is one of the course we are conducting. So with this, actually, it is end from my side.
Okay, sir. Thanks for your nice presentation, and I hope that all the participants has enjoyed your talk and they get all the related information this particular topic. And so I would like to thank you, sir, once again, and thank you very much for us accepting our invitation and delivering a wonderful talk.
Yeah. So thank you very much for our director, Dr. Lalit Kumar Avasti, so, sir,
Yes, sir.
and your chairman of this program, Dr. Tapas Palai, convener, Dr. Leela Manohar, coordinators, Dr. Arvind Kumar Gautam and Dr. Rahul Saab for giving the opportunity to share my work. So, and thank you very much for all participants for listening and interacting in question hour sessions. Thank you.
Thank you, sir. Thank you, sir. Thank you very much. Okay, so the next session we have from 2:30 onward. So we all will meet at 2:30. So we will take a break for lunch, and after that we will again assemble at 2:30, and we can have the next session. Yes.
और ये डाइट पे हम लोग